Welcome back. Today, we're going to go through a few examples of how to write the vector parameterization of a line. Let's do a quick overview of how this works. To get a vector parameterization of a line, we need a point P and then the direction in which we desire to travel for our line. So if our point P is right here, and we know that we want to travel in the direction of the vector V, we can use that to define an entire line R. And this line R is given by starting at the point P and then moving in the V direction by adding to it a scaled version of V, or something that's been multiplied by some real number T. Let's do a couple of examples. We're going to find a vector parameterization for a line that, in our first example, will pass through the point 2, 5, and also heads in the direction of -3. And then in our second example, we're going to have it pass through 2 points. All right, so in our first example, I always like to start just going back to the equation that we want to work with. So the equation that we're starting with is R equal to P plus T times our vector V. Well, we're given a point and we're given a vector. The point in this case is that 2, 5, and then our vector is 4, -3. And that's pretty much everything we need in order to be able to fill out this equation. So the answer for this one is really quite straightforward. We just plug in that 2, 5 plus, and then 4, -3 for V, and that gives us the vector parameterization for that particular line. Now for the second example, where we're passing through 2 points, and those 2 points are 8, -3, 5, and -1, 0, 9. Well, we go back to the same idea of starting with R equals P plus T times V. And we definitely have points that we could plug in for P, but we don't have V. But we do know how to get a vector using 2 points. And so that's exactly what we're going to do. We're going to take the vector that's defined by these 2 points, plug it in for V, and then use one of those 2 points for P. All we got to do is label these guys. It really doesn't matter what we call them, so I'm just going to call the first one P and the second one Q. And PQ is equal to -1 minus 8, 0 minus -3, and then 9 minus 5. So we're going to get -9, 3, and then 4 for my vector that's going to go in for V there. So now we're ready to start filling in that equation. P is 8, -3, 5, and then plus T times -9, 3, and 4. Another thing that we can do with these parameterized lines is we can determine whether or not 2 lines intersect, just like we can with a regular definition for lines. So let's look at that. So we're going to determine if the lines that are given intersect, and if so, we're going to find their intersection point. Okay, so the lines that we're going to work with are going to be R1 of T equal to 2, 0, 2 plus T times 0, -1, 0, and R2 T equals 2, 1, 0 plus T times 0, 3, 1. Okay, So actually, the baseline idea behind finding out whether or not these intersect is pretty similar to when we would work with just some normal functions or lines. So what we want to do is see if we can find some sort of inputs such that these two wind up being equal to each other. Now, unlike solving for the intersection point of a regular function, note that we actually don't want these two inputs to necessarily be the same. We're going to take s for one of them and t for the other. And we're actually going to rewrite these two so we can actually just compare their components directly, because that's how we tell whether or not 2 points are equal. I'm going to go ahead and replace t for s in our first case. The way I'm going to rewrite them is just by adding those two pieces together. So I'm going to get 2 and then negative s and then another 2 right there, and then r2. We can just leave the t there. That's going to become 2, 1 plus 3t, and then t for our third component. Now, in order to make sure that, in order to be able to solve for like s or for t, what our goal is to see if they intersect is to make the components match. So this is going to give us 3 equations that we want to solve. 2 equals 2. Well, that one's already done for us. Negative s is equal to 1 plus 3t, which comes from that y component right there. And then finally, 2 is equal to t. That one, the work's already done for us too. So we can take this 2 and plug it into t here, and we're going to get that negative s is equal to 1 plus 6, which means that s has to be equal to negative 7. So that means that R1 at negative 7 is equal to 2, negative 7, 2. And we also know that when we plug in t, we're going to get the exact same thing out of R2. So when we plug negative 7 in to R1 and we plug 2 into R2, we wind up getting the same point, which means that that's where they intersect at. So they do indeed intersect, and that is our intersection point.